On March 16, 3I Atlas made its closest approach to Jupiter, passing through the region where the planet's gravity exerts a strong influence on nearby objects. But when it passed without any measurable deviation beyond what gravity alone could explain, it seemed as though the chapter of 3I Atlas was over. But we were wrong. While its trajectory behaved perfectly, the data revealed something far harder to ignore. The object's estimated mass remained near 1 trillion kilograms, a value that defied expectations and refused to fit the model. The first step in understanding why this number matters is to consider how astronomers measure mass for objects that cannot be weighed directly. Unlike planets or asteroids that can be observed over long periods, or, in some cases, orbited to derive gravitational pull, interstellar visitors offer no such convenience. They arrive unannounced, travel at enormous speeds, and vanish just as quickly. For 3I Atlas, its mass had to be inferred from its motion, and specifically from the subtle deviations from the path gravity alone would dictate. These deviations, called non-gravitational acceleration, arise from a natural but remarkably effective mechanism: outgassing. Outgassing occurs when volatile compounds on the surface of a comet or icy object sublimate, turning directly from solid to gas under the heat of the sun. As material escapes, it carries momentum, and by Newton's third law, the object recoils in the opposite direction. This recoil is tiny but measurable over astronomical distances with precise tracking. By combining the observed acceleration with estimates of the mass loss rate and the velocity of the ejected material, astronomers can work backward to estimate the object's total mass. In effect, the object reveals its own weight by how it is nudged by its own evaporation. The process is elegant in principle, but fraught with uncertainty. Measuring the acceleration is straightforward enough, using repeated observations to track its position over time. But the other variables, how much material is being lost and how fast, must be inferred indirectly. Brightness changes can suggest the amount of material expelled, and spectroscopic data can reveal its composition. But these methods have margins of error. The velocity of the escaping gases is similarly modeled, rather than directly measured. Each assumption ripples through the calculation, creating a range of plausible masses rather than a single definitive number. To refine these estimates, researchers build competing models based on likely compositions. In the case of 3I Atlas, the main candidates driving sublimation are carbon dioxide and water. Carbon dioxide sublimates at lower temperatures, allowing activity even when the object is farther from the sun. Water, on the other hand, requires higher temperatures, becoming significantly closer to perihelion. Each model yields a different set of outcomes. If outgassing is dominated by carbon dioxide, the object's effective diameter could be less than 1 kilometer. If water contributes substantially, the nucleus could stretch to over 2 kilometers. The differences are not merely academic. They directly influence the inferred mass, the density, and the way scientists interpret its physical nature. These models also highlight a subtle but persistent tension. Some water-dominated scenarios require a surface area large enough to sustain the observed gas output, but that same area would imply a mass too large to produce the measured acceleration. The object would have to be simultaneously large enough to generate the gas, yet light enough to be nudged by it, a contradiction that cannot be reconciled without adjusting other assumptions, such as lowering density or increasing the velocity of the outflow. Certain high water production models can be ruled out entirely because they demand physical properties inconsistent with observations. Others remain viable only under a narrow set of conditions. What emerges is a landscape of plausible, but not definitive, solutions. Despite these challenges, a general picture does emerge. The mass of 3I Atlas is estimated to be on the order of 10 square kilograms, while its diameter likely falls between 1 and 2 kilometers. These figures are consistent with what is known about cometary nuclei in our own solar system. A density of approximately half a gram per cubic centimeter is typical for porous, icy bodies, and a nucleus of this size could naturally generate the observed non-gravitational acceleration. Viewed in isolation, the object is unremarkable. What makes it extraordinary is the context, how it compares to other interstellar visitors. The first such object, Oumuamua, had an estimated mass of only about 10 million kilograms. This means 3I Atlas is roughly 100,000 times more massive, a disparity spanning 5 orders of magnitude. Statistically, if interstellar objects followed a distribution similar to small bodies in the solar system, many low-mass objects should have passed through the inner solar system long before one as massive as 3I Atlas was detected. Yet observations tell a different story, suggesting either that our expectations about the population are flawed, or that our detection methods are heavily biased. And indeed they are. Observational surveys are inherently biased toward objects that are large, bright, or actively outgassing. Smaller or darker objects may simply pass unnoticed, reflecting too little sunlight to register against the background stars. Active comets, in contrast, produce visible comas or tails that make them stand out. In other words, the interstellar objects we detect are not necessarily representative of the population at large. They are the ones easiest to see. In this context, the apparent anomaly of 3I Atlas becomes less surprising. Its mass is remarkable only when compared against a limited and incomplete sample. Even within the estimated mass itself, uncertainty remains. The calculation depends on several assumptions: the velocity of outgassing, the rate of mass loss, the composition of the surface, and the asymmetry of the jets. If gas velocities are higher than assumed, the inferred mass is lower. If they are underestimated, the mass is higher. Even small changes in these parameters can lead to significant shifts in the final estimate. Until additional observational data are available, particularly high-resolution measurements of gas production rates, the precise mass will remain uncertain. Composition plays a particularly critical role. If carbon dioxide dominates, the smaller size estimates align more comfortably with the measured acceleration. If water contributes significantly, larger sizes and different densities must be considered. Thermal behavior, sublimation rates, and outflow velocities all interact to produce the observed motion. Refining these parameters is essential to narrowing the mass range, but doing so requires data that are difficult to obtain for a fleeting interstellar visitor. The broader significance of 3I Atlas is not in the numbers alone, but in what they reveal about our knowledge of interstellar objects. With only a handful of detections so far, the statistical framework used to interpret these objects is weak. Each new observation reshapes our understanding, revealing gaps in theory and exposing assumptions that had previously gone untested. What appears anomalous may simply be the result of limited data. Observational bias and model uncertainty combine to make rare events appear more extraordinary than they truly are. Yet the story is not merely one of numbers and models. It is also about method. The techniques used to estimate mass and size rely on a deep understanding of physics and careful indirect observation. Non-gravitational accelerations are small and require precise tracking over months. Gas production must be inferred from subtle changes in brightness and spectral features. Combinations of models, assumptions, and calculations are used to paint a coherent picture. The process is painstaking, but it demonstrates the rigor and creativity required to study objects passing through our solar system at tens of kilometers per second. 3I Atlas also underscores the importance of comparative analysis. The vast difference between its mass and that of Oumuamua highlights the danger of drawing conclusions from a small sample. Early detections may not reflect the full distribution of interstellar objects. They reflect the ones most detectable with current instruments. As more objects are discovered, patterns may emerge that reshape our understanding, revealing that what seemed exceptional is actually typical when viewed across a larger population. The encounter with Jupiter, initially expected to provide dramatic insight, confirmed only the obvious. 3I Atlas responds to gravitational forces exactly as expected. There were no hidden accelerations, no unexpected interactions. The anomaly lies not in its path, but in the subtle, cumulative effects of outgassing and the way these effects translate into a mass estimate. It is a quiet mystery, one that exists in the numbers rather than in a spectacular event. It challenges scientists to refine their models, improve their observational techniques, and confront the limits of what can be inferred from limited data. Looking forward, additional observations, both of this object and future interstellar visitors, will help resolve these uncertainties. More sensitive telescopes can detect fainter, smaller objects. Spectroscopy can provide better estimates of composition and outgassing rates. Long-term tracking will refine acceleration measurements and reveal more about asymmetry and mass loss. Over time, the apparent discrepancy in mass may be reconciled with a broader statistical understanding of interstellar populations. For now, 3I Atlas stands as a compelling case study, It is neither a violation of physical law nor a supernatural anomaly. Its mass, trajectory, and outgassing behavior are all consistent with known principles of physics. The tension comes from the interplay of limited data, observational bias, and the inherent difficulty of studying objects that travel between the stars at extraordinary speeds. It reminds us that science is as much about understanding the limits of knowledge as it is about discovering new phenomena. In the end, the true intrigue of 3I Atlas is its ability to illuminate the unknown. It is a bridge between systems, a messenger from afar, carrying information encoded in its motion, composition, and mass. Each data point challenges researchers to ask better questions, refine models, and anticipate what the next interstellar visitor might reveal. Its passage is fleeting, but its impact on scientific understanding endures. While the Jupiter encounter proved uneventful, the object's very existence and the quiet anomaly of its mass ensures that it will remain a subject of study and fascination for years to come. As new instruments come online and observational techniques improve, the narrative of interstellar objects like 3I Atlas will continue to unfold. Each passing comet or asteroid from beyond the Sun offers a rare window into material formed around other stars, carrying clues about their composition, structure, and dynamics. What seems anomalous today may become understood tomorrow, yet the lessons of careful measurement, model building, and skepticism will remain foundational.